Alright, so we're going to do a problem from chapter 12. The first problem we're going to do is problem 10. This diagram shows that the whole thing is in equilibrium, which means that the net force has to be 0, and also the net torque has to be 0 as well. With the string in the center exactly horizontal, block A weighs 40 Newton, and block B weighs 50 Newton, and this angle is given, that's 35 degrees. You want to find tension T1, T2, T3, and also this angle theta, okay? So, you have this two, the weight is given, the angle of this angle is given, but then these tensions are not given. So the first thing you need to do is draw a free body diagram. So now, the free body diagram should be at this point, because this is the point that has a lot of forces acting on it. So you want to find, draw a free body diagram for this point and that point to see how many forces acting on this at this point and that point, and set the net force equals to 0, because the whole thing is balanced. It means that the net force has to be 0. Okay, so let's see. When we look at this diagram, you can see that you have this downward experience WA, the weight of A. And at this point, the tension is away from the contact point. So you have the T2 that's pointing in that direction. And at this point, the tension away from the contact point, so the T1 is acting in that direction. So this is the free body diagram at this point. Now let's look at the point on the right. You can do the same thing. You have at this point you have tension that's pointing upwards. You have weight that's pointing downward, and you have the tension that's pointing that way. Okay, so this is the tension, this tension and that tension, they are T2. But then because you're looking at from different points, so the directions of T2 is different. Okay, so now we know that altogether there are 3 forces acting on this point, 3 forces acting on this point, and the whole thing is balanced, which means that the net force in the horizontal direction and the net force in the vertical direction have to be 0. So in other words, net X 0. Net y 0. So what are the forces in the horizontal? In the horizontal, we know that you have, let's look at this point, you have, look at this diagram. You have the rightward force, that's called T2, and T1 is pointing in that direction. So it has a positive y component and a negative x component. So you can solve the equation according to this diagram. So we know that the x component and this weight have to be balanced each other. And horizontally, this force and that force have to be balanced each other as well. So that's how you relate all these forces to each other. All right, so now this tension T2 is rightward, so T2, and then there's this T1 has an x component, which is opposite the angle. So minus T1 and then sine phi, that has to be equals to 0. Okay, and then vertically you have T1 cosine phi, because it is adjacent to the angle, and then minus WA, that has to be equal to 0. So we can see that WA is given, the angle is given, so you can quickly calculate your T1. Okay, so let's do that first. So you have your T1 that's equal to WA over cosine the angle. So WA is 40 over cosine 35. So your T1 should have the numerical value. Your T1 should have the numerical value of 48.8 Newton. Okay. Once you have your T1, you can plug into this equation to find out your T2. So your T2 is equal to T1 and then sine phi. So you have 48.8 times sine of 35. So you should have your T2 that has a magnitude of 28 Newton. Okay. So this is your magnitude of T1. This is the magnitude of T2. So now we are ready to tackle on this point. This one, T2 is not given, theta is not given. So T2 is not given, but we already calculated T2. So we can apply Newton's law again at this point. So rightward. So T2, if you look at this diagram, the T2 also has an upward y component and the rightward, and it has a rightward x component. Okay, so this, this is T3. Okay, so you can see that this T3, the x component of T3 has to be balanced by T2, and the y component of T3 has to be balanced by the weight of block B. So we can solve the equation according to this diagram. So in the horizontal component, you have T3 T3 times, again, the horizontal component is obviously the angle, so sine theta. T3 sine theta has to be equal to T2, okay? And then T3 cosine theta, the y component, has to be equal to block B, okay? Block B is given, so you can see that we can quickly, let's see, because here T3 is not known, theta is not known, so you can actually just do, manipulate the equations a little bit. So T3 get canceled here, so you have the tangent theta on the left-hand side, and that's equal to the ratio of T2 over WB. So T2 we calculate to be 28, and WB has a magnitude of 50. So you can calculate your theta just based on this equation. So theta, after you do the calculation, your theta is equal to 29.2 degrees. So after you do the, after you calculate your T2, after you calculate your theta, then you can, you can plug into this equation to calculate the T3. So this equation and that equation doesn't really matter. So you have your T3, and then sine of 29.2, and that's equal to T2, and your T2 is equal to 28. So you can calculate your T3. So your T3 should have a numerical value that's 28 over sine of 29.2. You got 53.3 Newton. Okay? So you can see that, based on this diagram, because everything, the net force in the horizontal direction and in the vertical direction have to be, zero. So you can set up equation according to the Newton's first law. Okay, that net force equals to 0, and then just find out how many forces acting at this point, how many forces acting on a point, and set your equation accordingly. Then you should be able to find, what you're asked to find. All right. The next one, we're going to do problem 15. And let me just erase this. This chapter 12 is all about forces. Net force equals to 0, and net torque is equals to 0. And so, so you just need to find out how many forces acting in the horizontal direction and vertical direction. And for torque, just find out what the net torque is. Okay, so this is the diagram for problem 15. Let's see, so this is point O, this is point P. We apply force right here, that's your F1, and F2, so this is your F1, and your F2 is applied right here. And from this point to this point, this is your A, and from this point to that point, that's also your A. And at this point, at this end, a third force is applied, and the separation between this O and P, that's your D. And it says that, so this is your point P. And it says that there is a force acting on this, that's your FV. And there's a force rightward, that's your FH. And we have we're given, let's see, so from this point to that point, that's your C. From this point to that point, to the second force, that's your B. Okay, and that's your A. All right, so A, B, C, let's see. So let me just write down all the numerical values. So your A is 2 meters, B is 3 meters, C is 1 meters, F1 is 20, F2 is 10, and F3 is 5 Newton. All right, so problem 15. So we have these three forces acting on the structure showing the overhead view. So this is the top view. we wish to put the structure in equilibrium by applying the fourth force at a point such as P. So this is the point where we want to apply force. The fourth force has a vector component, the Fh and Fy, which is the vertical component and the horizontal component. We're given the ABC and the three forces magnitude. So we want to find the magnitude Fv, the magnitude Fh, and also where should we place that fourth force. Okay. Now the key point here is that everything is balanced. So the net force has to be 0, and the net torque also has to be 0. So that's how, whenever you do this kind of problem, the easiest way is to find out what are sum out all the forces in the x direction and in the y direction, and then set it equal to 0 and to see what we get. And then if you if after you've done all this, you find that you still the information is not sufficient enough for you to find other information, then you have to use torque. Okay. So now let's see. Horizontally, so again, the key point here is that net force in the horizontal direction is equal to 0. The net force in the vertical direction is equal to 0. So let's see how many forces in the horizontal. Horizontally, we have this F2 that's pointing rightward. We also have this horizontal force, unknown force that's pointing rightward as well. So these two add up and has to be balanced by this third force, because it's pointing leftward. So you have the F2 plus Fh, and that's equal to F3. You can see that I already dropped the vector sign because this is rightward and this is leftward. So this two, the rightward force has to be balanced by the leftward force. So in this case, your F2 is 10, your Fh, and then that's equal to F3. F3 is 5, so which means that your Fh is 5 Newton. Is that right? Am I missing something? F1 is here. Yeah, this is rightward. This is rightward. I'm sorry. F2 is downward. I'm sorry. F2. Let's see. F1 and F2 is downward. So Fh. So the only thing that's in the rightward direction. So this is rightward. Sorry, downward. So the only forces in the horizontal direction will be Fh, which is positive, and that has to be balanced by F3. And that's to the left. So your Fh is 5 Newton. Okay. Now vertically, you have F1 that's pointing downward. You have 2 that's pointing downward, and then you have the outward force that's Fv that's pointing upward. So your F1 plus F2 has to be balanced by Fv. So this is how you calculate your Fv. So F1 plus F2, so that's 20 plus 10, so that gives you 30 Newton. So this force, this applied force has a horizontal component that's 5 Newton and has a vertical component that's 30 Newton. So it's very straightforward. And then you also find the separation. Where should you apply this force? So in that case, whenever distance is involved, you'll have to use net torque equals to 0. Use that condition in order to find out where should you apply that force. Okay, so we're going to set up the equation. So I'm just going to, so let me just write down here that Fv. We already found that Fv now is 30 Newton, and your Fh is equal to 5 Newton. So now we're going to utilize the condition that the net torque is equal to 0. Okay? How do we calculate torque? Torque, of course, is R cross F, the moment on times the force magnitude. So in order to calculate torque, you need to pick a point to calculate your net torque. So where do we want to find that? Where do we want to find that reference point? We can use this point as our reference point to calculate torque about that point. I mean, in fact, you can just pick any point, but then we can just pick this one as and then to calculate the net torque. So if we pick this one, the first force that because F1 is directly applied at that point. When you have a force that's directly applied at that point, that force does not contribute to torque. So F1, you don't even have to, it's not even in the equation because it does not contribute to torque. And also anything that's along the radius do not, anything that's along the radius does not contribute to torque as well. So in other words, F1 and Fh, they do not contribute to torque. Okay, so F1 and Fh, do not contribute. Okay, produce zero torque. Okay, so they are not even in the equation. So this is this one you don't have to consider. The FH you do not have to consider. Now the only forces that you have to consider is this one. This is your FV that is perpendicular to the moment on. Likewise, your F2 is also perpendicular to the moment on. So FV and F2 you have to consider. And you have your F3 that's also, that's apply a distance from the moment on. This is the moment on, but then F3 is, moment on is the distance between the force and the moment on, the vertical distance. So the distance between the force and the moment on is this. So you can just, so we have the moment on for F3. So we can set up the equation according to this, what we just said. So the first term we consider is FV. So R cross F. The moment on here is this. This is, this is the distance. So that's your B. So you have your B, and then times FV. Okay, and then sine of the angle. The angle between them, of course, is 90 degrees because this is upward, and your radius is draw the extension. That's your radius. So they are perpendicular to each other. What about direction? Does it produce a positive torque or negative torque? So this is your R. This is your F. So you can use R cross F. So point your finger in the directions of radius, and then sweep your finger toward the second toward the second quantity. So your thumb gives you the directions of the torque, and it's outward, which means it's positive. So we'll just keep it as positive. Okay. So plus. So I put a plus here to indicate it's positive quantity. So you have the moment on times the force magnitude. Now let's move on to the next force. The next force is located right here. So the moment on will be from this point to that point. So this is your F2. So I'm going to just move the vector downward so that it's easier for you to apply the right-hand rule. And this is your moment on, okay? So this is your R. So you have R cross F. So again, point your finger in the directions of R, sweep your finger toward the second vector, and you can see that it produces net torque. So you have to put a negative in front of it. And the distance. The moment on is from this point to that point. The distance is B. So you have your B. So wait. Sorry. So the distance between. So you have your B and then times your F2. Now this is not B. The distance between this and this vertical force is D. So that's your D. Sorry. So that's your D, because this is the origin. And this is from this point to where you apply the force. The separation is D. Now for this F2, the separation between this point and that point, this is your B. Okay? And then the next force is your F3. So F3 is applied. F3 is applied to that to that direction. So this is your F3. And your moment on, it is the vertical separation between the force and this radius. So this is your A. So you have the term that's A times F3. Now, what about the sign? So F is pointing in that direction, and your R is pointing in that direction. So you have R cross F. So point your finger in the directions of the force, and then sweep your finger toward the second force. So you produce a negative torque. So you have the negative sign in front of it, and the whole thing is equal to 0 because you don't have any other forces. F1 does not contribute, FH does not contribute, and FV contributes to this turn, F2 contributes to that turn, and this is your F3. So you can see that F2 and F3, they contribute to produce a negative torque, and FV produce a positive torque. So plug in the number, we should be able to find out what the D is. Where should you apply that force? So you have your D times your FV, which is 30, minus your B, and your B is 3 times your F2. Your F2 is 10, and then minus your A is 2, and then F3 is 5. And the whole thing is equal to 0. So in that case, your D is equal to, this is 10, this is 30, so it's 40. So it's 40 over 30. So you should get your D, that's about 1.3 meters. Okay? So you can see that this is basically you apply Newton's first law and then find out the forces as much as possible, and then you have to use net torque equals to 0 to find out where you should apply that the force. And so for this one is straightforward R cross F. So just the separation. The separation between the where you apply force and the reference point times the magnitude of the force. And likewise for F2, that's magnitude and the separation is your B. Now for F3, because it's applied at a distance away from the radius point, so this is your moment on, that's just A, okay? Or you can use the R cross F and then some sine theta, but then you have to actually figure out, what the theta is. So in this case, visually, you can just see that that's just the vertical separation, so you can just use the magnitude A. Okay, so that's that. And the next one we're going to do is problem 28. All right, 28. Let's draw the diagram first. All right, so let's see, problem 28. So suppose the length of the uniform bar is 3 meters, and its weight is 200 newtons. So because it's uniform bar, so the mass is at central mass. Let the block's weight. So you have a block that weighs 300 newtons, and the angle here is 30 degrees. The Y can withstand the maximum tension of 500 newtons. So this is the maximum tension that it can that you will have. What is the maximum possible distance x before the Y breaks? So you want to place this block so everything is balanced, so it does not break. With the block placed at this maximum x, what are the horizontal and vertical components of forces on the bar from the hinge? Okay, so the hinge here is going to provide support. So let's first of all find out how many forces acting on this system. So we know that you have the weight of the block, you have the weight of the bar, you have the tension, and that's not sufficient enough. The hinge right here is going to provide support. And the directions of the support is that it will provide an upward force and the rightward force. So this is your FH, and this is what we call the FV. Okay, so this is the force applied to the hinge. Why do we know that the horizontal force has to be this way? Because you have the tension that's, you have a tension that has a component that's a leftward. It has to be balanced by a rightward force, otherwise it would not be balanced. Okay, so once we have that, then we are ready to apply. So that's that's arrange the order first. Let's find out all the forces component, and then we'll find out where the block should be placed at the position x. Okay, so net force has to be equal to 0. Then in the x and y direction. So let's see how many forces in the horizontal direction. Horizontally, you have your FH. That's rightward. And then this tension has a rightward direction as well, but it's has S component, but it's pointing in the leftward direction. So you have the tension, so it's minus tension, and then the S component is cosine 30, and the whole thing is equal to 0. And so that you can see that your FH can be easily calculated because it's just 500 times cosine 30. So once you do the calculation, let's see, do I have that? So you just have 433 Newton. So that's the horizontal component. The y component is equal to 0. So you have an upward force, you have two downward forces, and then this one, this tension also has the upward, y component as well. So you have your Fv plus tension times sine 30, and then that minus W block minus W bar. The whole thing is equal to 0. So your Fv is basically equal to 300 plus 200 minus tension, which is 500 sine 30. And so you should have the numerical value that is equal to 250 Newton. Okay, so you can see that just by you applying Newton's first law, we are able to find out the force magnitude. The vertical force has 250 Newton, and the horizontal force has 433 Newton. So now the question is, where should you place this block so the whole thing still remain constant, balanced? So which means that the net torque has to be equal to 0. And so the net torque, whenever we want to find net torque equals to 0, you want to find you want to pick a point that you want to pick the your reference point and then calculate torque about that that reference point. So you can choose this one. Why do you want to choose that one? Because when you choose this one, your Fv and your Fh, they do not contribute to torque, because this one is those two forces directly apply at the origin, so they do not contribute to torque. And this is so that you can make your the equation set much easier, because you don't have to consider these two terms. Okay, so now let's see. So so what are the forces that will contribute to torque? You have the weight of the block, the weight of the bar, and also this tension. These three forces going to contribute to torque, and you add them together and set it equals to 0. Okay, so let's see. If the block is placed at this point, which is position x, so the moment arm will be x, and the weight will be W block. So that's the magnitude. That's R cross F. What about the direction? So this is the origin. So your R, this is a vector, so we can extend this. So that's your R. This is the moment. This is the direction of the radius, and this is the direction of the force. So R cross F. So R cross F. You can see that thumb is pointing into the whiteboard, which means that it produces a negative torque. So you should put a negative sign in front of it to indicate that it produces a negative torque. Okay. So you will do the same thing for the weight of the bar. Now the bar is at the center of the bar, so the distance, so the moment arm is just L over 2, the length divided by 2, and then omega times and then W bar, the weight of the bar. And what about its direction? So this is the moment on the direction of the radius, so you do the R cross F. So R cross F, and you can see that also is negative. So you can see that when it comes to weight, it's almost like you produce negative torque, okay, and so that you have that, okay, and it will depend if this in this arrangement. So now you have this x is unknown, this is given, and all these are given. We have one last term we have not yet considered. That's your t. So R cross F. So you should have your R, and R here is the total length from this point to that point. So you have your R cross F. So you have R is L, and then your F is T. And then R cross F is equal to RF sine theta. So sine of, what is the angle between tension and the radius? This is your radius. So you can see that the angle between them is between your R and T. So that's 180 degrees minus 30. So you have 180 degrees minus 30. Okay? So that's the magnitude. What about direction? Direction, we use R cross F, so you have your R cross F, so it's positive, so put positive sign in front of it, and you set it equals to 0. So now we're ready to plug in the numbers. So you have negative x, the weight of the block is 300, minus your L is 3, so you have 3 over 2, and then times the weight of the bar, which is 200, and then plus the length of the bar, which is 3, and then tension is 500, and then sine of 150 degrees, and the whole thing is equal to 0. So you can see that we have everything except x, so we can calculate our x, and our x, after you do a calculation, you should get 1.5 meters. Okay, so in other words, the maximum place that you can place is at 1.5. If you place a little bit, farther away, then the whole thing will not be, sufficient to support the thing, and this this wire is going to break. Okay, so that is that.